Hi, thank you for joining us for Microsoft Research Summit 2021. I'm going to be presenting my work, Maia Chess, a human-like neural network chess engine. So I'm a PhD student at the University of Toronto. I'm also doing this with Siddhartha Sen at Microsoft Research, John Kleinberg at Cornell, and my advisor, Ashton Anderson at the University of Toronto. So just a quick overview. I'm going to be talking about why we want human-like AI, why chess is a good way to study it. Then I'll be talking about our two papers. So first of all, our first paper that introduced the Maia Chess, and the second one that built on that and went from targeting skill levels to targeting specific players. And then finally, some of the value of having scientific artifacts that are useful to a broader community. So I think most people watching this will sort of be aware that every year, machine learning AI systems are getting better. So in image processing, for example, handwriting recognition is nearly or better than humans, depending on the language. You can do translations of thousands of words a second on some systems. But, for example, in translation, the outputs might not be that human. So there's a need for systems that are aware of humans. Sort of the biggest example of this might be self-driving cars, where you have these AI agents that have to interact with the world with humans in it. There's also medicine, where you want systems that output results that are understandable to doctors and sort of trusted and don't make surprising decisions. Or, I think as talked about in this summit, you want to be able to model humans for video games or other sort of interactive systems where you need to understand and predict what human behavior will be like in the system. So that sort of gets to our main research questions, which is how do we bridge the gap between artificial and human intelligence? So to do that, we decided to study chess. So why chess? First, it has this long history of use in AI. So Deep Blue beat Kasparov in '97 and sort of one of the first examples of computers becoming superhuman. Additionally, there's AlphaZero, which sort of brought reinforcement learning to sort of the forefront of public awareness when it beat humans in Go. It also was the strongest chess engine for a time when it beat Stockfish in 2017. So we have these sort of wonderful superhuman AI systems in chess. So there's Leela Chess Zero, which is an open source implementation of AlphaZero, and there's Stockfish, which is open source, sort of more traditional chess engine. And so both of those are available freely to use by researchers. Additionally, we have these wonderful large data sets. So in this work, we're using Lichess, which has this database of 2.4 billion chess games, all available for download, and they're easy to use. And then one of the other wonderful things about chess is the community is diverse. We have players from all over the world, many different languages, and we have this useful measurement of skill. It's usually called an ELO. It's basically a number. The higher the number, the better you are at chess. So 1,000 is quite a weak player, 2,000 is a strong player, and around 2,400 is where grandmasters are. And we're sort of looking at AI systems to interact with humans in chess. And first of all, do we need to do this? And we sort of surveyed what the existing landscape was, and we discovered that most of the existing chess engines aren't very good as teachers. They really can just say what the correct move is. They don't actually provide sort of a useful explanation. They can't sort of behave like humans. So if you want to play against them, you have to give them a strong handicap such that they will basically let you win in some way. So that sort of got to our primary research question, which is how can we algorithmically capture human style in chess? So can we build a chess engine that behaves like a human in chess? So what does this mean? The way we define this is we're trying to predict the next move a human will make on a specific chessboard. So a human is playing chess and they look at the board, what next move do they make? Not sort of have the same skill level. In fact, we want to make it so our models have an awareness of skill, so we can predict the moves of players of different skill levels, because sort of by definition, players of different skills will make different moves. And what we want is what you see on this plot here. So on the x-axis is rating, and on y-axis is this move prediction accuracy. So we want to have some sequence of models or parameterization of models that lets us target a specific rating. So we started by looking at Stockfish and Leela chess. So Stockfish is sort of the strongest traditional engine. It uses heuristics, isn't really machine learning, more of an expert systems type approach. And we found it does decent at predicting high skill players, but for weak players, it doesn't do very well. Additionally, we found this sort of interesting result where the very weak version, so a very limited minimax search, actually is more accurate at predicting moves than a sort of moderate minimax search. But as you go to even deeper search, it does better at predicting the next move for most players. Then the other sort of competing model was Leela Chess Zero. So this is an implementation of Alpha Zero. It was sort of considered to be very human-like, and our results sort of bear that out. It is generally a bit better than Stockfish at predicting the next move, particularly for weaker players. But both these models, you can't target the ratings of a player. So that gets to our model, which we called Maia. So we were both able to get higher accuracy by training it specifically to target player move prediction. And we were able to create a parameterization where we have different models that target different skill levels. So our Maia 1100 is the best at predicting the moves of 1100 rated players, whereas Maia 1900 is better at predicting 1900 rated players. So to bring it all together, our models were both about 10% more accurate, and we're able to target specific player ratings. And we were sort of happy to see that even if you go to higher rated players, our models still exceed the other models by a decent margin. Although Stockfish slowly is starting to reach up higher. And so our system was based originally on AlphaZero, the self-play formulation with UCT, UCB1 based algorithm for reinforcement learning. And we spent months trying to find if we could improve our accuracy, or basically assuming we had to use reinforcement learning to solve this task. And in fact, after some work, we discovered that basically the reinforcement learning algorithms, as soon as you tell them to optimize for winning the game, they do that too well, basically. And they start playing much stronger games than any of the players we're targeting. So by removing the reinforcement learning from our models and doing it as a simple classification task, we were able to get a significant improvement in our accuracy, actually. So then building on that, we want to see if we can, instead of capturing at a player rating level, can we capture for a specific player? So this work was also done with Russell Wang, who just graduated from the University of Toronto and starting his master's at the University of Berkeley. So we called this Transfer Maia. So this is using fine-tuning / transfer learning technique. And as you can see here, we sort of compared it to all our pre-existing models, and we got a decent amount of uplift. So if you plot on the left here, you can see our nearest Maia. So this is our previous work's accuracy on the x-axis, and then you compare that to our new model's accuracy on the y-axis. So basically being above the diagonal is an improvement. And we found about a 4% improvement by targeting specific players. Additionally, we found you get a slight benefit by having more games. So we required about 10 to 20,000 games before we started getting significant improvements, and even more games is better. One of the nice sort of results of this, though, was we can use this to predict who a player is. So if we take a set of games from an unknown player and we run every single model on it, and you look at the accuracy on those games, the most accurate model, 98% of the time, is the player, the model is the same player. So you can use this to identify players with about 100 games. So sort of finally, one of the results of our work is we have these chess engines. So these are actually things that we were able to host on Chess and have them available for the community to play. So this is great. We got over 1 million games played against our models. We also have lots of community feedback. So we have a qualitative sort of analysis that supports our paper's hypothesis that our model is very human-like. The community seems to agree with that. Additionally, we have a mailing list with lots of people on it. So we're using that right now to set up for future work and particularly some surveys. So in conclusion, thank you for watching this. I hope you will consider having your AI systems be more aware or trying to understand humans. And if you want to get in contact with me, my email address is shown here, and we have a website with more information about this project. Thank you.